Okay, for my Advanced Algebra Trig Honors students, I'm making a couple of podcasts with some example problems that I think will help you as you get ready for the test on exponents and logarithms. So today's topic, doubling and half-life problems. Okay, so we're going to start out with three pretty standard, straightforward questions about how long it takes something, in this case money, to double. So the first question is on the board right here, and you have $500. It's earning 6% annual interest, and you want the money to double. And so the equation that we're using, and just as a reminder, the equation is always the same when we're doing exponential models. And then the base in here, right, this is b, and b is going to be 1 plus r when the b is growing, and 1 minus the rate when it's decaying. So I'll go ahead and put a b in there, and hopefully that will make sense. All right, so in the first situation we have $500, so that's our initial amount, and the rate it's growing at is 6%, so we always change that to a decimal, and we put it in that form. And then the question is, how many years will it take to double? So that's asking, when will the 500 turn into 1,000? All right, to solve this equation, we're solving for the exponents. So in our mind, we're thinking the only way to get that exponent down out of the air is to take the log at some point. So before we do that, we need to get rid of that leading coefficient. When we divide both sides by 500, oh look, surprise, we get 2. And so this is the equation we're solving. So if you have that fancy software, you will take log base 1.06 of the 2, and what you get when you do that is 11.896 years. Okay, just a note here that if you don't have the software, then the method you would use at this point is you would take the log of both sides, you'd get the same answer. Now just to make sure that everybody's clear, what we found is that if we take the 11.896 years and substitute it in for t, when we do this problem we should end up with $1,000. So it's always a good idea when you're doing these kind of problems to check your answer. And it's really easy to check. Okay, good. The next two are going to be similar, so let's get through these. This time we have $700. We're increasing at a rate of 5%, and we want to know when that value will double. Okay, again, the first step is to get that leading coefficient on the right out of the way. So once again, we get 2. The base is 1.05 to t. We change that immediately to log base notation. 1.05 is the base, 2 is the argument, and when we put that in our calculator, we get a value 14.207 years. Okay. All right. Last one we'll do. This time $900 is invested at 20%, so we're going to add 0.20 to 1. Set that equal to double the amount, and probably you're getting the idea that you really don't need the 900 and the 1800, that as long as the ratio is 1 to 2 here, then you can simply go right to 2 equals 1.2 to the t. Okay. And so when we do the log base, again, 1.2 of 2, this time we get that it's going to take 3.802 years. Now, just as an aside here, I might ask you to take this information and this starting amount and rewrite the exponential equation as a doubling equation. All right? So then you would say P of t is equal to, same amount to start with, now I'm doubling, and if it takes me 3.802 years to double, then my power is t over 3.802. Okay, hopefully that makes sense. Let's go on to some half-life questions. See how they're very similar in how we do it. This time we give us a we're given a starting substance, starting amount, and then instead of increasing by a rate, we're decreasing. So we have 500 milligrams, we're decreasing by 8%, and we want to solve for t when we get to half the amount. All right, so step 1 is to divide out that 500. We're not surprised when we get 1/2 equals 0.92 to the t. We do log base 0.92 of 1/2, right? And we get 8.313 hours. Okay, so what exactly did we find? What we found was that it would take 8.313 hours for the 500 milligrams to be cut in half if the hourly rate was 8%. So just like the problem we just did, we can write the same equation, this one, as a half-life problem. We can say that the amount we're left with is the amount we start with, and this time our decay factor is 0.5, and then instead of to the t, it's to the t divided by 8.313. Okay, let's do one more of these and see, hopefully this will make it a little bit clearer. We have 4,000 milligrams. We're decreasing by 15% an hour. Oh, and I changed to X in the middle of it. And I want to know when, at what time, we'll get to half that amount, right? So we divide by the 4,000 and we get 1/2 equals 0.85 to the t. We change it to log notation, put it in our calculator, and for this one we get 4.265 hours. All right? Okay, good. Last one, I don't think we need to go through it. The milligrams has changed, now only decreased by 4% per hour. Why don't you try that one and see if you get the answer I get, which was 16.980. Okay, great. I hope this video was helpful. The next video will do the same types of problems, but in reverse. I'll give you the half-life and the doubling time, and you'll have to turn it into a daily or hourly rate. Okay, see you in class.